this get-together, and I appreciate the invite of the three associations here. And also thank you very much for coming. I hope this is working. Can you hear me in the back?
Yes.
All right. Appreciate your coming to this event on Sunday. Initially, and they wanted me to come here on Saturday, and my response was thank you very much, but I changed my work behavior. I used to work 7 days a week, but recently I reduced it down to 6 days a week. Okay, so I work from Sunday until Friday. Now, in the introduction, and a terminology was mentioned, bucky paper, and that's outside 3D printing, but I would like to just spend a few seconds to explain what bucky paper is. I spent the last 15 years of my life working on a nano material called the bucky paper, and it was made from carbon nanotubes or carbon nanofibers, and some of you might have heard carbon nanotubes before. About 15 years ago, I've got my first piece of bucky paper. It's a film. It's a thin film of nanomaterials, and the thickness is about 20 or 30 microns. The first piece of bucky paper I got was from Dr. Smalley. He's a 1996 Nobel laureate, and he passed away a few years ago, but he was at Rice University. So he gave me this piece of bucky paper and said, well, Ben, can you infiltrate this bucky paper with polymer resin to make a laminate, making composites? Okay. So we did. So that was the genesis of my 15 years of effort and working on trying to make bucky paper from about this big to rolls of bucky paper, material. So that's a different story. Okay. So if you are interested, we can talk about it some of the time. But today, it is 3D printing. I wanted to give you a little bit background about myself. So forget about what you heard in the introduction. So this is a more important. I'm relatively new to Georgia Tech. I joined Georgia Tech in January 2012. Before that, I spent almost 20 years at Florida State University, not very far away from Atlanta, in Tallahassee, Florida. And before that, I spent about 10 years at Iowa, University of Iowa, and also State University of New York at Buffalo. And you might have heard of SUNY Buffalo. So in the last 30 years, I've been doing teaching, research, and also administration. I joined Georgia Tech less than 2 years ago as the director of Manufacturing Research Center. But last year we changed our name from Manufacturing Research Center to Georgia Tech Manufacturing Institute to reflect our expanded mission. So Georgia Tech Manufacturing Institute, or GTMI, covers the entire Georgia Tech. So 6 colleges. Some of you may be working at Georgia Tech or affiliated with Georgia Tech. But Georgia Tech has 6 colleges, and the GTRI, that's Research Institute, and also there is an organization called the EI Squared. That is our business outreach organization called the Enterprise Innovation Institute. So our incubators, our venture lab, ATDC, and manufacturing extension programs, all of those programs are housed within the EI Squared. So that's the business commercialization arm of Georgia Tech. At Georgia Tech, we have 7 university-level institutes. So one is manufacturing, that is GTMI. We have 1 materials, 1 nano, 1 in energy, 1 in paper. Georgia Tech is big. Georgia is big in the paper space, and we have 1 in people and technology. And I think I'm missing 1 more. Robotics. Okay, so we have 7 institutes at the university level. If you look at Georgia Tech, we have about 300 research centers. Some centers are really large, several hundred people. And some centers are really small, 1 professor and 2 graduate students. And we call them Eagle centers. So we have about 300 centers across the campus. And it is very confusing to the people within Georgia Tech, not to mention it's very confusing to people outside Georgia Tech. So if you want to have some relationship with Georgia Tech, where do you start? Who you contact? Okay, so the university level, 7 strategic institutes are like 7 doors. If you are interested in manufacturing, so GTMI is the door that you get in. Now, if you're interested in robotics, and then you just knock on robotics, and then that institute will introduce you to the people who can help you, okay, to have a relationship with you. So that's how we set up at Georgia Tech. Now, before I go any further, I would like to introduce Christopher Oberste. And Christopher is a PhD student in material science and engineering. And he is our internal guru on 3D printing. At Georgia Tech, we have several labs, not just one, several labs across different colleges in the broader space of 3D printing or additive manufacturing. And today I'm going to use 3D printing and additive manufacturing just back and forth. And technically they are different, slightly different, but today let's just treat both the same. All right, so just for the sake of simplicity. So let me start right now. Mr. Lee has listened to this is your 3rd time, so actually he can close his eye and then recite my presentation. I built this slide myself. In fact, I treat every presentation very, very carefully and very seriously. And because I think people come and listen to you talk, and you really want to respect. They really drop their work and then come here and spend a couple hours. And you really want to give them at least some value out of the time they spend in here. So that's why at the beginning I really appreciate that you're coming here. You may be wondering why I have these photos here. I built this myself. This one is entirely built in 3D. It's a metal powder designed and built at Oak Ridge National Lab. Okay, you can see after you can see. And this one was designed and built by a Georgia Tech graduate. Dr. Lonnie Love is working at Oak Ridge National Lab. And this one is a additive process using electron beam to melt material in order to solidify the materials. So we'll get to know different technology later. This one uses laser, and this one uses ultrasound to prepare some printing inks, like inkjet printer, okay, to prepare some inks to atomize it, and before they begin to push out of a nozzle. And this photo shows several of the turbine blades made with additive manufacturing technologies. And this is a Nike shoes made with 3D printing, and also some printed electronic circuits using this technology. So that is really what I would like to cover this afternoon. So let's begin the presentation. I have quite a few slides, so sometimes I will go really fast. Again, most of the materials here are done not by myself. Okay, so I really want to give a proper recognition of the people who actually contribute to this deck of slides. And there are too many people to list all of them, but needless to say that I would like to appreciate my students, staff, and faculty at Georgia Tech Manufacturing Institute, and also Georgia Tech in general, and the U.S. Army, Navy, Air Force, and also Defense Advanced Research Program Agency, called DARPA, and also Oak Ridge National Lab, and also the National Additive Manufacturing Innovation Institute. So there are several other organizations, parties, and people that perhaps I forgot here. 3 things I would like to cover this afternoon. The first one is I would like to just create a context for 3D printing. So 3D printing doesn't exist in a vacuum, in a silo. There is a context where 3D printing creates value. Okay, and that context is manufacturing, especially advanced manufacturing. And the second one is the manufacturing we're talking about here today is not the same manufacturing that we used to know thousands of workers under one roof on assembly line and trying to push product out. Okay, so that is much more like a labor-intensive manufacturing. But the manufacturing we're interested in is more like advanced manufacturing, or sometimes we call it manufacturing 2.0. And third one is 3D printing. It's game-changing. It's game-changing. It's going to change many, many things around us. But there's a ton of work that we need to do before 3D printing becomes pervasive everywhere, right? So, point number one, why manufacturing matters. This is a very important subject matter when Mr. Lee introduced me at the beginning, and I'm really proud that all my professional life I have been working in manufacturing from a labor-intensive all the way to advanced manufacturing. In the last, I would say, 15, 20 years, manufacturing actually was very much ignored, okay, in the U.S. One very famous quote, some of you might have heard this before. At one time, he was under President Bush, not the Bush Jr., but Bush Sr., and he was chairing the National Economic Council. And he made a very famous quote, of course he regretted, I hope he regretted, is that he says, computer chips and potato chips, what's the difference? All right? So $100 of computer chips and $100 of potato chips is still $100 of chips. And it was a big mistake because to make a computer chips you need high tech. But to make a potato chips you may not need high tech. But perhaps I'm wrong. Anyway, so I'm very delighted to see that manufacturing is coming back to the U.S. because it is required for every nation, every country. Okay, Chinese, Germany, UK, US, Australia, Japan, Korea. Every country needs a very strong manufacturing base. Whether manufacturing is 25% of the GPA or it's 50% of GPA, it's up to that country to decide. But no country can survive and do well without some manufacturing activities, that's for sure. Okay? So let's look at the US. In the US, manufacturing accounts about 12% of the GDP, gross domestic product. So that's the total output within the country. But 70% of the exports from the US to the rest of the world come from manufacturing. Okay, so it's very important, you know that export is one of the very few ways we build wealth of the country, right? Now, if you consume everything that you produce without selling it to other people, if you look at your account balance, it stays the same, right? You may have food, you may have some other things, but your account balance will not increase. Your account balance will increase is when you sell stuff to other people, and people pay you cash, or give you a check, hopefully the check is good, all right? And then you begin to accumulate your balance. So that is the importance of the exports. Okay, the exports, 70% of the exports from the US to the rest of the world come from manufacturing, even though it is only a very small slice of the GDP. So that's number one. And number two is the return on investments. For every dollar we invest in manufacturing in the US, I think we see about $2.50 of the activities in the whole economy. So this is a very good return on investment. Okay, nowadays, if you can get 3% of interest rates, you are very happy, right? Now we're talking about 250% of returns on investment. So this is a very, very good investment in the state, in the United States. Especially, these activities drive very good jobs. We call them middle class jobs, not really a very low service type jobs. And third one, this one is amazing. I think that will surprise you. 90% of the patents in the US come from manufacturing. Okay, so this is amazing. Even though manufacturing accounts about 12% of the whole economic activities, but 90% of the patents, which is somewhat equivalent to innovation, not exactly, but somewhat, okay, come from manufacturing. So if you look at manufacturing drives wealth, manufacturing drives jobs, manufacturing drives returns on investment, and manufacturing drives innovation. So manufacturing is very critical if a country wants to be strong and strong. All right, so that's the context of the 3D printing and manufacturing. Now the second thing is manufacturing we're talking about today is different from the old manufacturing. More than 2 years ago, in June of 2011, so that's 2 years and several months ago, the White House announced the Advanced Manufacturing Partnership. Okay, the goal is really to bring back manufacturing and try to create a stronger manufacturing in the U.S. and in turn try to drive the job creation and drive the job retention. So the White House created a steering committee of 18 members, 6 university presidents, and also 12 CEOs of large U.S. corporations. So this was announced more than 2 years ago. And the Georgia Tech president, Dr. Bud Peterson, some of you might know him, and he actually was on the steering committee. And if you look at the rest of the universities, I mean, these are really top-notch engineering schools. I don't have to repeat. Okay, so these are really outstanding, like who's who in engineering. And then look at these companies. So even though I didn't start until January 2012, but Dr. Peterson and Dr. Cross, my boss, who is the Senior Vice President for Research at Georgia Tech, asked me to spend some time before I got here. So I was appointed to the Operations Committee for the Advanced Manufacturing Partnership. So that's how I got invited to the White House and different departments for different forums and workshops. So the purpose is really to get manufacturing back on track. The steering committee actually wrote a big report published last July of 2012, and it's online, and you can access to it, in which the committee mentioned 11 cross-cutting technologies. 11 cross-cutting technologies, meaning very important, not just for aerospace, not just for potato chips. Okay, so cross-cutting meaning it is useful for different industry, for different sectors. And then McKinsey actually published the reports earlier this year in May 2013, in which they also mentioned several cross-cutting technologies, very important to advanced manufacturing. And then also published this year, the Council of Competitiveness and McKinsey, it was Deloitte, okay. They jointly published a paper on the Global Competitiveness Index. They also have their own list of technologies. And there are several other reports in the past 2-3 years. And the reason I mention these reports is because one technology is consistently among the top 10 or top 15 technology. That is our topic of the day. Okay, so that's additive manufacturing. So what you see here is something that cannot be produced using the current manufacturing technologies other than additive. Okay, so look at the all this little grids and meshes there, and with also the number of flexibilities without machining and without much assembly. So this one was done entirely in 3D printing, and I think I circulated a part over there. That, Mr. Lee there, if you haven't seen it, feel free to use it. And that whole piece was done in one setup. Okay, so we didn't make different parts and assemble them together, glue them together. That's all done in one setup. Now, if you think this is really too industrial, and this one is perhaps more personal, okay, again, the evening gown is made entirely with 3D printing. Okay, so it shows how pervasive the process is. And now, if you read the news online or in the paper form every week, you see some articles about 3D printing, right? It's almost everywhere. But I think what I'd like to do today, that is my responsibility, is really to give you really the current state of the art, and also what is possible, and also what are the hypes, okay, that are reported in the news media. I want to give you a more balanced report on 3D printing so that we begin to know if there's a path forward, and if there's a path forward, what should we do in order to overcome the obstacles. So my tagline for the third topic is 3D printing is going to change a lot of things that we do, but there's a lot of work that we have to do first, okay? So start with a basic definition. So just exactly what is 3D printing? I've been talking for about 15 minutes. I have not explained what 3D printing is. So here is a definition. 3 steps, very simple. First part is you design, you prepare. So we call it pre-processing. You design your part. Okay, could be that part I just circulated, could be that evening gown, could be that robotic hand, could be the bottle, the cap here. You design it in a computer-aided system. I think all of you have heard use it, even develop your own CAD systems. You design your part, and then you let the algorithm slice your part into pieces. And each slice is about 100 micron thick. Okay, so you take a bottle, and you can do it vertically, you can do it horizontally. So it's up to you how you want to set it up. Okay, so each slice is about 100 micron. So think of it, you have a deck of poker, okay, a deck of cards. And then each card is sent to the second phase of the processing, to your printer. Why is it called a 3D printers? Because the current printing is printing on 2-dimensional paper, right? It's 2-dimensional. So we do 2-dimensional one at a time, and then there is a print head will print that card on a platform. Okay, so that's 100 microns, and second card comes 200 microns, the third one 300 microns, all the way until you have a bottle, you have a robotic hand, or you have your evening gown. Okay, so that is really the process. Most reports and news articles stop right here and treat it as if 3D printing is so simple. You design, you print, and you can go to your party. Okay, it's not that easy. There's a third step most of the papers don't talk about. Is a post-processing. In fact, that is the most time-consuming part of it. If you ask Christopher, and he likes this part, he loves this part, he hates this part. Okay, because this part is very time-consuming. It's a lot of tedious work. You have to clean up the parts before you can show it to other people. Okay, so most articles don't really talk about this one, and they say, well, you designed it, you printed, you're done. In fact, you have to clean it up. So that's the reality. Okay. So let me show you a quick video produced at Oak Ridge National Lab. The quality of the lab is really not that great, but I think you get the idea. All right, so I'm going to talk from here, and this is really, let me back up a little. Okay, it's called Arcam. Arcam is a company in Sweden. Okay, so this is a Swedish company. They produced a direct manufacturing printer. The technology they use is called the electron beam. Use a very high energy to melt material and to deposit material. Okay, so Arcam is the name of the company. So here is an airplane, 4 engines, and each engine has numerous turbine blades like this one. Now, if you are involved in machining manufacturing, you know that to make this blade is not easy. Okay, and according to traditional method, you either cast it or you forge it. But that is just the first step. And then you have to machine it, most likely using 4 or 5 axis CNC machine, computer numerical control machine tools. Okay, so it's not easy. You need a highly trained technician in order to run the part. But with 3D printing, we can do it differently. Okay, so I stop here because you can see that a computer algorithm actually slices it. Okay, so each slice is about 100 micron thickness. So this is all done virtually on a computer system. So once it's completely sliced, and the file will get sent to a printer, which is in this case is made by Arcam. All right, so you can see that right here there are two tanks. Each tank is filled with metal powders. The reason we have two, one on each side, is it goes back and forth, so we can save time in depositing the materials. Okay, so you can see some metal powder here, and then we prepare the material, heat it up, and then there's a laser there. So the first layer is deposited. So it shows microstructurally how the materials actually change their morphology and structure. So the second step, third step, so it goes back and forth until you have a blade. So it shows that it grows, okay, as the time goes, and then it created. You can see the platform lower and lower to accommodate the growth of the part. So this is what a 3D printer looks like by Arcam. All right, so this is what you get out of a 3D printer. So it doesn't look really pretty, and doesn't look like a turbine blade, but this is a post-processing. Again, the cartoon makes it look really easy. Okay, actually it's just very difficult. All right, so that's the video. So now you get the ideas. You design, you print, and you clean it up. And if you look at cleaning and carefully, is that you use, for instance, a air to blow the salt or the loose the metal particles away, right? And the hope is you can reclaim the material and can put it back in the tank and then reuse it. But most of the materials have been subjected to this high temperature environment. So microstructurally they have changed. So they are not like a virgin metal powders. So how do we reclaim the materials so that you can use it with the original material together? That is a big issue. But very few people actually talk about it in open literature. But if you are a businessman, you of course care about the raw material cost. And that is a big issue. That is a big issue. Okay, but most professors don't really care about it. They just produce it. See, we have a good part. Okay, and look at the dimensional stability. All right, so technically we can put additive into 4 different categories depending on the material that we use. The first is plastics. Actually, the plastic 3D printing started about 25 years ago, and it was called the rapid prototyping. Okay, some of us a little bit senior or more experienced remember this rapid prototyping from about 25 years ago. Started actually in the United States. But then the people look at the plastics. I mean, they look interesting, but we cannot use it directly on any serious applications. So the technology sort of ignored in the US and then moved to Europe. And actually the Europeans brought up the technology to a level they can process metals, they can process ceramics, and also printed electronics. And then if you look at across the bottom, these are the different energy sources that we can use to process the material. For instance, we can use lasers, most popular one, or we can use electron beams, very popular for metal. And we can use ultrasound to prepare the materials for printed electronics. Most people, when they talk about 3D printing, they focus on the first 2, sometimes maybe ceramics, but very rarely do people actually mention printed electronics, which I think is a mistake. Printed electronics should be part of the big family of additive manufacturing. So what are the applications in addition to the turbine blades, a robotic hand, and even guns? So these are the applications. Aerospace, okay, so you just saw a video from the engine parts to the turbine blades to many other parts, ducts, and connectors. And then for cars, actually, it's similar. many different applications, but my view of the difference between automotive and aerospace is the following. In aerospace, if you are making a batch of, say, hundreds of parts, that's high volume for aerospace, right? But in automotive, you have to make 1 million, so you say that's high volume. Okay. If you look at additive manufacturing, is more suitable for low volume production than for high volume production. So it will be inconceivable if we see people begin to 3D print all the cars, okay, from Chevrolet all the way to Porsche. Okay. So for automotive application, I believe additive will be used initially in making molds and toolings, jigs and fixtures in mass production. Okay, so it's different. Okay, so one is for the direct printing parts, and one is printing of molds, toolings, jigs and fixtures. Okay, and third one is medical and the biomedical applications. If you look at what 3D printing brings us, is really not you can buy one a few $1,000s, put in your garage, and you print a lot of keychains. 3D printing, the most important part is you can produce highly individualized parts, because you can design it and then you can print a part, you can change it slightly on the computer, then print it again, assuming that the whole path is all correct. Okay? So what can be more individualized? Human beings, right? So we have like 50, 60 people here. Every one of us have different size, different shapes, different style, different things. So 3D printing, and I see it, one of the major applications is going to be medical and biomedical applications. So that is where we see the most benefits. Not just the commercial benefits, but also the societal benefits of 3D printing. And the fourth category is repair and maintenance. Just as a reference point, the U.S. Navy, when they have an aircraft carrier go out for, like say, 9 months, they carry a bunch of parts, because there are so many different aircrafts, and each aircraft has so many different parts. Like Boeing 787 has 4 million parts. Okay, and you don't know ahead of time which part is going to break, right? So you need to be prepared for some broken parts. So what do? You carry as many different parts as you can. Okay, just make sure that it's all covered. But after a tour, 9 months, you come back, and then you look at, you only use 5% of it. So you carry 95% of the parts you don't actually use. So what if you have several 3D printers on the aircraft carriers, and if a part is broken, you print one, you repair it. So you really reduce the amount of inventory you need to carry around, okay, for really nothing. I mean, seriously, right? So that's repair and maintenance. Of course, the ideal situation is if your car is broken, you need different parts you can print in your garage, and then you can replace it easily. That may come one day. For instance, I don't know if anybody is working for Delta. Anybody working for Delta here? Okay, Delta has they call it technical operations, or tech op operation here. Delta tech op maintains its own aircraft. In addition, they also maintain the aircraft for about 150 airlines around the world. Okay, because they have the scale of economy here, so they can provide a service. But many other airlines, they just don't have that need to have their own operation, so they outsource it to Delta. So Delta has reached a point where they don't really want to buy parts from GE or from Pratt & Whitney or from Rolls-Royce or Siemens. They want to build their own parts. Okay, so that is very interesting. They want to change their business model. So think of it, it's going to change many things, and we'll get to that quickly. All right, so this is the fourth member in the additive manufacturing family, called the printed electronics. Why is this important? Again, let's look at small volume production. I know in China and also in Korea, in Taiwan, in fact, in this in Asia, is very important. Very important industry is semiconductor, right? Making chips, computer chips. Okay, so the foundries, using today's U.S. dollars, if we want to create a brand new foundry, the capital investment is about $8 billion U.S. dollars, okay, to create a foundry. Now, if you are making parts for iPhone or Samsung phones or other phones, very large volumes, I think the cost can justify, no, the volume can justify the cost. However, if you are dealing with aerospace, defense, or other companies or the repair aftermarket, you are not talking about tens of millions. You are talking about thousands, maybe hundreds, a few parts. In that case, I don't think you really want to invest in $8 billion in the foundry and to make a few hundred parts. Okay, so that is where additive printed electronics comes in. You buy a machine, you design your circuit, and you can print the circuits right there in your lab. Okay, so printed electronics is very, very efficient and cost effective. Now, it is somewhat similar to inkjet printing, but very different in how materials or the inks are prepared. In inkjet printing, so you have droplets. Okay, so you just spread it and you drop it. So if you look at the ink come out of the nozzles like a cone, so you cannot control the resolution is really not very good. However, for the aerosol jet, it atomizes the ink, and then it uses the air to direct the flow, almost like a straight line. So if you look at the cross section here and here is almost the same. So it's like a straight cylinder as opposed to a cone. Okay, so in that way we can control the resolution, which is about 10 microns. And also another advantage is it has a very good standoff distance. It's about up to 10 millimeter here. So what it means is that the nozzle and your substrate, that is the material print your ink on, can have up to 10 millimeter. That's very good.